Alright, good afternoon everyone. So I am Vincent Villahuerta, and for today I will be discussing with you all about Markov chains and one of its applications, which is on internet search engines. Right? So before we proceed to the discussion of Markov chains, let's just introduce first a concept which is called a dynamical system. Alright. To define it, a dynamical system is a finite set of variables whose values change with time. So to illustrate, what are some of these examples of a dynamical system? So first, currencies, foreign exchange rate. We know that these values change every day throughout time. Sometimes in seconds these values change. Also weather. Sometimes today is sunny, tomorrow will be rainy. So that is one example of a dynamical system. Okay. The value of these variables at a point in time will be called the state of the variable at that specific time. And then the vector that will be formed from these states will be called your state vector. So we will be using the term state vectors all throughout the lecture or the discussion. Okay. Now, let's have an illustration. Let's have a problem just to illustrate the concept of a dynamical system. Alright, so during Christmas season, we know that people are going to malls frequently. Alright, so from a survey, it was observed that at the first week of the season, 35% of the shoppers choose small A, while 65% choose small B. Okay, since both malls offer different promotions throughout the seasons, the choice of the shoppers might change. So after a week, it was observed that 25% of the shoppers from Mall A wanted to move to Mall B, and 40% of the shoppers from Mall B want to transfer to Mall A. So how are we going to illustrate that in a graph? So let's have a blank page here. So let's create two circles, one for each mall. So let's say this is small A and this is small B. Okay, so from the given earlier, we know that after 1 year or after 1 week, 25% of the shoppers from mall A wanted to transfer to mall B. So if this is 25%, we know that the remaining 75% will still shop at mall A, right? And for the other one, 0.4 or 40% of the shoppers want to transfer from mall B to mall A, and that would mean the remaining 60% will still shop at mall B. Alright, so this will be our graph after 1 week of the Christmas season. Alright, okay, now let's proceed. So for the solution, we have this defined state variables, state of the variable. So we define x of t x sub 1 of t as the percentage of the shoppers who choose small a at time t, and then we define x sub 2 of t as the percentage of shoppers who choose small a at a time t. Alright, okay, so we define first the initial state vector or the initial value of these two. So at time equals 0, we note that from the given, there are 35% of the shoppers are in mall A, and for the mall B, there are 65% of the shoppers, or 0.65 of the shoppers are in mall B. So this is our initial values now for the two variables. Okay, how are we going to write that as a state vector? So we can write it as an x of 0 equal to the vector or to the column vector containing x sub 1 of 0 and x sub 2 of 0. And our initial state vector would be the column matrix 0.35, 0.65. So this will be our initial state vector. Okay, so now let's observe what will happen after 1 week. No? So how will these values change after a week? Okay. So let's solve first for mall A. So after 1 week of mall A, or after 1 week, what will happen to the percentage of shoppers in mall A? Okay. From the earlier diagram, we know that 75% will remain at shopping in mall A. So 75% of the initial, which is 0.35, and then we add the 40% of shoppers that transferred from mall B. So if we add that, that would be plus 0.4, and the percentage of shoppers in mall B initially was 65%. So we will add that one. Okay, and for mall B, after 1 week, how many percentage, or how many what's the percentage of the people that will transfer from mall A to mall B? It's 25% of the shoppers from mall A, and then 60% now will remain of the original shoppers of mall. No, this is 60%. Okay, of the shoppers of mall B. Okay. So what do we observe now? We can observe here that this can be written as x sub 1 of 0, and this one as x sub 2 of 0. Okay, so before that, we solve it first. So we'll get here 0.5225 and 0.4775. Okay, what do we do next? We can say that at x of 1, or the value of the state vector at time equals 1, would be, can write it as a column matrix. So we have this x sub 1 of 1 and x sub 2 of 1. That would be equal to the multiplication of the matrix 0.75, 0.25, 0.4, 0.6 times 0.35 times 0.65. So what we did here is that we wrote down this linear system as a multiplication of two matrices. Okay, so what do we observe here? We notice here that to get the state vector at time equals 1, we just multiplied this square matrix to the initial state vector, which is this one. Okay, so that's what happened. So how can we derive a general formula for all the remaining number of weeks now? So we say that to get the future state vector k plus 1, we just need to multiply this matrix. So later we will name that matrix now to the previous state vector, which is the initial, not necessarily initial, but the previous state vector, which is x sub 1 of k times x sub 2 of k. Alright, so this will be the formula in getting the future state vectors. Okay, so let's further solve. So if you want to observe what will happen over a 5-week period, so this is what will happen. So we want to get x of 2, or after 2 weeks, so we will still use the same matrix. So 0.75, 0.25. We will now multiply it to the vectors of x of 1, but x of 1 is 0.5225 and 0.4775. If we multiply that, we will get 0.583, 0.417. So that means at the state vector at time equals 2, we will have this column matrix. Okay, and proceeding, we will have x of 3, And for x of 3, we will now use the previous state vector, which is x of 2. So we have this. We will use x of 2, or the earlier result, which is this one. And we will get, using a calculator, no? So we will get 0.604, 0.396. Okay? And then we'll do it several more times, but I'll just show the answer. So for x of 4, we will have 0.614 and 0.389. And for x of 5, we'll have 0.614, 0.386. So we'll now interpret now. So it means that after 5 weeks, this is the state of the percentage of the shoppers at mall A and mall B. So that means 61% of the shoppers are at mall A, and almost 39% of the shoppers are at mall B. Okay, so that's the state vectors for a 5-week period. Now let's observe what will happen if we extend the number of days, or the number of weeks. So let's see what will happen after 15 weeks. So solving using a calculator, no? I have here 0.615, 0.385. Okay, and then last, let's try 20 years. So if we extend the time to 20 years, this is the state vector. It will be 0.615, 0.384. So what happened here? We noticed that as we go closer, or as we have a bigger number for the value of time, the values for, or each value for the state vector seems to stabilize, no? So for the value of x sub 1, it stabilizes to 0.615, and the value for x sub 2 stabilizes to 0.384. So it means that as our t becomes larger, we see a pattern, no, that it stabilizes. So we will discuss that further later. Okay? Okay, now. So we'll now introduce what a Markov chain is. So dynamical systems that deal with probabilities are called stochastic processes. Okay, so what are these stochastic processes? So for example, we have a marble in an urn with 4 yellow marbles, 3 red, and 3 are blue. So what's the probability that we get a yellow? We can just say that we have a 4/10 probability. And what's the probability of getting a red? We have 3/10, and probability of getting a blue is just 3/10. Okay, so actually these probabilities can be written as a state vector, no? Because that's the chance, or that's the initial probabilities, no, when you put all of them in an urn. So we say that x is the probability, so we can write that as 4/10, 3/10, 3/10. So this one is a state vector of this problem. Okay, and we say that, to be specific, this vector that has non-negative entries add up to 1, no? So yung elements na nag-add up to 1, so we say that this is a probability vector. Kasi nag-add sa 1 yung values ng ating column matrix, or yung state vector. Okay? So, balik tayo dun sa example kanina. We know that we have this matrix, diba? 0.75, 0.25, 0.4, 0.6. Okay. So, these percentages might not represent the total number of shoppers, but rather, these are just the probabilities or the chances that shoppers choose mall A or mall B. So, the experiment earlier is not, hindi talaga sure kung yun yung dami ng tao na pupunta sa mall na yun, but that's just an estimate of the probability or how likely the persons will shop at that specific mall. So, yun yung sinasabi ng mga percentage na to. And what's special about this matrix is that we can also say that this matrix is a stochastic matrix. Bakit siya stochastic matrix? Okay, so let's look at the columns. If you add up the values of the columns, they will all add up to 1. So, if it adds up to 1, all the columns, no, we can say that this is a stochastic, this represents a stochastic process. Okay, so ayan. Now let's define formally what a Markov chain is. So a Markov chain is a dynamical system whose state vectors at a succession of equally spaced times are probability vectors, and for which the state vectors at successive times are related by an equation of the form x of k plus 1 is equal to the square matrix P times x of k. So this looks like the equation that we had earlier, no? To get the state vector of the future, you have to multiply a square matrix to the present state vector. Okay? So that matrix P will now be called the transition matrix for this dynamical system. Okay? So let's proceed. So suppose that, let's illustrate the Markov chain through an example, right? So suppose that tomorrow's weather in Baguio relies on today's weather only. So tomorrow's weather will be only affected by today's weather, not the previous day's weather. Okay, the graph below shows the probabilities of the changing weathers. If today is sunny all throughout the day, observe the weather for each day in 1 week. So I will first show you the diagram, so I'll just draw it for you. So we have three weather types. So we have the sunny, the foggy, and the rainy. So if today is sunny, there's a 60% chance that tomorrow is sunny, 20% chance that tomorrow is rainy, and 20% chance that tomorrow is foggy. Okay, if it's raining today, there's a 50% chance that tomorrow is still rainy, 40% chance that tomorrow is foggy, and 10% chance that tomorrow is sunny. And then last, if today is foggy, tomorrow has 70% chance of being foggy again, 20% chance of having a rainy day, and 10% chance of having a sunny day. So this will now be the relationship between the sunny, rainy, and the foggy weathers. Now, how are we going to create the transition matrix now that will represent this graph? Okay. So let's create now the transition matrix. So let's say that's P. Since we have three variables here, sunny, rainy, and foggy, we will have a 3x3 square matrix. So for the columns above, we will write that as from, because that's your state of origin. So we have sunny, foggy, and rainy. Then we will go to the next day, and that will be the rows sunny, foggy, rainy. Okay. So what are we going to put in the entries of this matrix? Okay. So if today is sunny and tomorrow is sunny, what's the chance? No? So according to the diagram, today is sunny, tomorrow is sunny. What percentage is that? That's 60%. So that's going to be 0.6. Okay. And next, if today is sunny and tomorrow is foggy, what's the percentage of that occurrence to happen? So today is sunny, tomorrow is foggy, there's a 20% chance. Okay, so that's how you write down the transition matrix given the graph. So I will just write down all the entries. So we have 0.6, 0.2, and 0.2, 0.1, 0.7, 0.2, 0.1, 0.4, and 0.5. Okay, and to verify now that this is indeed the transition matrix of this dynamical system, you add up all the entries and you will definitely get a 1 for all the columns. Okay, so we now have the transition matrix P. Okay, so I'll just write that down again. Okay, so according to the problem, today is sunny. So what will be the initial state vector if today is sunny? We can just write it as x sub 1, x sub 2, x sub 3. And we say that x sub 1 is the variable for the sunny day, x sub 2 for the foggy, and x sub 3 for the rainy. Okay, so if it is 100% sunny today, the initial state vector would be 0, not 0, it would be 1, 0, 0. Alright, so that will be our initial state vector. Okay, so let's compute the probability, Okay, sorry for the interruption. Let's continue. So, okay, this is now our initial state vector. Okay, so we want to check what will happen after 1 day. No, so using the formula that we have mentioned earlier by the Markov chain definition, we multiply the transition matrix by the initial state vector, or by the current state vector. So we multiply it by 1, 0, 0, and by matrix multiplication we would get 0 0.6, 0 0.2, 0 0.2. So it means that if today is sunny, there's a 60% chance that tomorrow is sunny, and 20% chance that it will be foggy or rainy tomorrow. Okay, let's observe what will happen in a 1 week period. So x of 2, so to get the state vector at time equals 2, we will use the same transition matrix. Okay, but now we will use the state vector at time equals 1. So we will now use 0 0.6, 0 0.2, 0 0.2. Okay, so what will happen to the result? We will have 0 0.4, 0 0.34, and 0 0.26. So you see, the values are really changing depending on the state vector of the at the previous time. Sige. Let's fast forward. So let's just check what x of 7 is, or what is the state vector after a week. So by method of calculation, I got 0 0.20, 0 0.508, 0 0.286. So what does this represent? So it means that after a week, 50% of those days must be foggy. No, because we are sure that somehow the values will stabilize after some number of days, and we can see that it's most likely stabilizing at 50% foggy. So we will see later. We will verify if this is really the percentages. Okay, now let's have Markov chains in terms of the powers of the transition matrix. So we have observed earlier that in a Markov chain with initial state vector, which is x of 0, the successive state vectors are x of 1, and to get x of 1 we multiply p to x of 0. To get x of 2 we multiply p to the previous state vector, which is x of 1, and x of 3 is equal to p times x of 2. Okay, and we can also write actually x of k as x sub k. So para mas madali. Now, these successive state vectors can be written again in terms of the initial state vector only. Okay? So bakit? Bakit siya nangyayari? In the x sub 1, we know is equal to p times x sub 0. Okay? And x sub 2, we know that it's p times x sub 1, but from the previous equation, we know that x sub 1 is just px0 or px sub 0. So we can multiply p by px sub 0 and we will have p squared x sub 0. So here we can see that x sub 2 is written in terms of the initial state vector. Okay? And next, to get the third state vector, x sub 3, we multiply p by x sub 2, and from the previous equation, x sub 2 is p squared x sub 0. So p cube, x sub 3 is just p times p squared x sub 0, which is p cube x sub 0. So from this, we can define a pattern. So it follows that x sub k is just p raised to the power k times the initial state vector x sub 0. Okay, so this is one way of getting state vectors at a time equals k. Okay, so let's verify, no? So kanina we want to show x sub 7, no? So we want to verify if we will get the same value. So x sub 7 is just equal to the transition matrix 0 0.6, 0 0.2, 0.2, 0 0.1. Okay, and we raise it to 7 times the initial state vector, which is 1 0 0. And then if I use my calculator to solve for it, I will have 0 0.20, 0 0.508, and 0 0.286. Okay, which is just the same as this previous result. Okay, so that definitely makes our life easier because we don't have to use the previous state vector anymore. But the challenging part here is multiplying the matrices, no? Or raising a matrix to a power. So a calculator will really be helpful. Okay, so how about x sub 30? So if we want to solve the state vector after a month, no, after 30 days, hindi na natin pwedeng gamitin yung initial equation because we will do it 30 times. But instead, what we can do is just to apply the formula that we have derived earlier. So we will just have this 0 0.6 we just raise it to 30 times the initial state vector, and what will be the result? So using our calculator, so I will have here raised to 30, I'll have 0 0.2, 0 0.514, 0 0.286. So what do we notice? We see that after a month, it actually stabilized to 0 0.2, 0 0.514, and 0 0.286. So that means we are sure that it's going to be 50% foggy most of the days. So that's how prediction works, no, using Markov chains. All right. Okay, let's just discuss some concepts that involves Markov chains. Now, so we can define a matrix that doesn't stabilize. So let's consider the matrix here, P 0 1 1 0. This is a stochastic matrix now because if you add all the columns or the values of the columns, it's still 1. And it can be used for a Markov chain. Okay, let's observe that if we square this matrix, we will get the identity matrix. So that means the identity matrix is equal to P squared. And if we get P raised to 4, we know that it's still the identity matrix. And all the even powers of P will give you the identity matrix. Okay. Now, P, if you cube it, you will get P. If you raise it to 5, you will get the same matrix. So, for odd values of the powers of p, you will get p. Okay, so the successive states in the Markov chain will be x sub 0, px sub 0, p squared x sub 0, but we know that p squared x sub 0 would be ix sub 0 because p squared is the identity, and it will just be x sub 0. Okay, and then next, this is supposed to be p cubed x sub 0, but p cubed we know is the same as p. So anong nangyari dito? We know that x sub 0, px sub 0, this is x sub 0, and this is px sub 0. So it doesn't stabilize, no? Nag-oscillate siya from x sub 0 to px sub 0 to x sub 0 again, and then to px sub 0 again. So this is one type of matrix which does not stabilize. Okay? And that will lead us to a definition that will be useful later. So we define what a regular stochastic matrix is. So a stochastic matrix P is said to be regular if this matrix or some positive powers of this matrix has all positive entries, and a Markov chain whose transition matrix is regular is said to be a regular Markov chain. So let's see later what's the use of regular stochastic matrices, no? Okay, let's go back to our previous examples. So these are some examples, no? If A and B are these matrices, square matrices, we say that these are regular. Why? Because all the entries are positive. There is no zero entry. Okay. But for example, if we take this matrix P, 0.5, 0.5, 1, 0, can we say that it's not regular just because there's a zero entry here? Hindi pwede tayo mag-deduce agad. What we can do is to square it. Tignan nyo, after squaring it, we get this square matrix. 0.75, 0.25, 0.5, 0.5. Okay, so there exists a power that has a non-zero entry. So we can say that this matrix P is indeed regular. But for this one, since we know that all the powers of P will have 0 in it, we can definitely say that this matrix P is not a regular stochastic matrix. Okay, so we cannot use that later, no, in the theorem that I will discuss. Alright. Okay, so from the book, we have this definition, or we have the theorem that involves regular Markov chains. So the theorem 5.5.1 states that if P is the transition matrix for a regular Markov chain, then first, there's a unique probability vector Q with positive entries such that PQ is equal to Q. So this Q satisfies the equation. Also, for any initial probability vector x sub 0, the sequence of state vectors x sub 0, p x sub 0, p squared x sub 0, and so on will converge to the vector Q. And then the sequence p squared, p cubed, and p raised to k converges to the matrix Q, of which each of the column vectors is Q. I know. So let's see how this theorem is helpful. Okay. So what is a steady state vector? So let's see. The column vector Q being discussed in the theorem is called the steady state vector. So for example, we have a regular Markov chain. No? We say that this vector Q satisfies this equation. Okay. Now, if I move Q to the other side, I can have this equation, and I can factor out Q by having I minus P times Q. And here, we can say that Q is an eigenvector corresponding to the eigenvalue of 1 of the matrix P. Okay, so dito makikita natin application eigenvectors and eigenvalues. Okay, so magamit natin siya later to get the steady state vector. Okay, let's go back to the problem earlier about the shopping problem. Okay, So for the shopping problem, we know that the transition matrix is 0.75, 0.25, 0.4, 0.6. Okay, so if we use the equation to get the steady state vector, we have I minus P times Q is equal to 0. So we will have this equation. So we have 0.25, negative 0.25, negative 0.4, and 0.4 multiplied by the elements of Q, which are Q sub 1 and Q sub 2. We solve for the null space. So solving for the null space, I will not show all the computations, but we will have Q1 is equal to 1.6 Q2, and Q2 will be our free variable. Okay, so what is the solution space? We have 1.6 S and S, and this is our Q. But we want to get the exact value, right? So what to do to get the exact value? So since we know that Q is a probability vector, the sum of the elements must be 1. So 1.6S plus 1, S would be 2.6 S, which must be equal to 1. So therefore S must be 1 over 2.6. So if we solve for Q using S equals 1 over 2.6, we will get Q equals 0.615 and 0.384. So as we have observed, no, this is the vector that the state vector is earlier stabilized to. So nagsastabilize yung value niya dito sa dalawang column at sa dalawang entries ng column vector na to. Okay? So that's the purpose of the steady state vector. We can predict saan magsastabilize yung values ng ating state vector. Alright. So that is for the shopper problem. Okay, now let's proceed to an application of a Markov chain, which is on internet search engines. Okay, so let's define what web surfing is. So from the book, there's a problem that Alice and Bob has to solve now. So assume that Alice and Bob are each given a set of 6 web pages containing keywords on a topic of common interest. Each has his or her own strategy for establishing an order of importance for the pages. So let's discuss first the strategy of Alex. So she said that networks of links or references between the pages can provide a means of measuring their relative importance. So she created a diagram called the web graph. So this is how the web graph looks like. So how do we interpret this? So for example, page 1. Page 1 has outgoing links to page 3. Where else? I think it's just page 3. No? Okay, that's one example. So for page 2, ano yung mga outgoing links niya? It has outgoing links to page 1 and page 5 and page 4 and so on. So we define that as a directed path. A directed path from the ith page to the jth page means that the ith page has an outgoing link to the jth page. So this is the relationship of the links of each page. So she will proceed as follows. Now, so first, she disregards links to or from pages outside the 6 given pages. She disregards links from a page to itself, and she disregards duplicate links. She also assumes that there are no dangling pages or pages that has no outgoing links. Okay? So to summarize the data, so here you can see no, initially she is at page 2. Okay? Kasi yun lang yung may value. So after 20,000 clicks, these are the number of clicks that each page got. Okay? But let's express it as a fraction. So because we are dealing again with probabilities, so after 20,000 clicks, you will see that the values here stabilized to these values. Okay? So how do we relate that to the page rank? So by looking at the fraction, we will see that page 3 is the most viewed, then followed by page 6, 1, 2, 5, and then lastly 4, which is the least viewed. Okay, so how do we apply the Markov matrix in this Alice strategy, in the strategy of Alice? So we have noticed that as the total number of mouse clicks increase, the fraction at which each page is visited starts to stabilize. So the limiting values of these fractions, called page ranks, can be taken as a measure of the relative importance of the pages. This method of Alice may only work for small web graphs. So yung 6 pages, it can be considered a small web graph. But for example, we're talking about the whole internet now. This process might actually be more complicated. Okay, so we first define the adjacency matrix of a web graph with n pages to be the n by n matrix whose ij entry is 1 and the j page has, if the j page has an outgoing link to the ith page and 0 otherwise. So for example, this one, this is page 1, 2, 3, 4, 5, 6. So from and to. So from page 1 to page 1, 0, because there's no link from page 1 to itself. But here, page 1 to page 3 is 1 because there is a link from 1 to page 3. So that's how you create the adjacency matrix. So another one, for example, if you start at page 2, from page 2 to page 1, there is an outgoing link. So we denote it by the arrow here. So ganun lang. So that's the adjacency matrix. Now, by definition, if a web graph with n pages is served by clicking a mouse, then the state vector x raised to k is the n times 1 column or n by 1 column vector whose ith entry is the probability that the server is on the ith page after k random mouse clicks. Okay? So if from the earlier, we are certain that Alice starts at page 2. So what will be the corresponding state vector? It must be 0, 1, 0, 0, 0, 0. Okay. So if we take the product of ax raised to 0, we will have this. And what's the result? The result is 1, 0, 0, 1, 1, 0. How do we interpret that? It means that after clicking a mouse, there's a possibility that page 2 will go to page 1. This is page 1, 4, or 5. So there's a chance that the server is on these 3 pages. Okay? But you notice here, this is not a stochastic matrix because the sum is not equal to 1. So what do? We introduce what we call a probability transition matrix B associated with an adjacency matrix A. So here, basically, we just get the probability of each column. So from matrix A, from the adjacency matrix A, we will transform it to the matrix B. So how? So we just add the values of the column here, and then we divide each entry by that quotient. So for example here, the sum is 1, so you divide 1 by 1, so the entry is just 1. Here, the sum is 3, so you divide each entry by 3. Okay, do you understand? So also here, the sum is 2, so you divide each entry by 2, so you get 1/2. So that will be your probability transition matrix. Okay, this matrix B incorporates the probability transformation information for advancing randomly one page to the next with a mouse click. So suppose again we start from page 2. The state vector is this, and after one mouse click, we will get this. And if you notice, the result is now a stochastic matrix, which means that there is a 33% chance that she will go to either page 1, 4, or page 5. Okay? So the successive mouse clicks will form the sequence shown below. And then the following successive state vectors will be like this. And if you notice, if we get x raised to 15, it starts to stabilize in accordance to the table that we have seen earlier. No? So let's also define the steady state vector, which is the eigenvalue equals 1. No? So yun yung nagko-correspond dun sa ating matrix. So if we solve for the steady state vector, we will have this, and comparing it to the table, it actually corresponds to the values of the steady state vector. So nagsastabilize dito yung ating values. And that's how Alice's strategy works. Okay? Now, for Bob's strategy, what is the problem that Bob considered? So there are two problems here, no? One of which is, what if the pages are enclosed to page 1, 2, 3 only and 4, 5, 6 only? Paano pag magkahiwalay sila? Also, what if, in this case, there are no outgoing links from 1, 2, 3 to page 4, 5, 6? So, lahat sila papunta lang sa 1, 2, or 3. Walang palabas ng 1, 2, or 3. So, paano na solusyonan ni Bob yun? He introduced what we call the damping factor. So, Bob's solution to the problem is to assume that he is not required to follow the links on the current page, but with a certain probability lang of delta, which is the damping factor, he can go to the next page by choosing a link on the current page and some probability, which is 1 minus delta, that he will choose the next page at random. So, may chance na, kahit maliit na chance na makapunta siya dun sa page na hindi pwedeng matouch ayon dun sa web graph. Okay? So, the new probability matrix will be given by this M, capital matrix M. So, we have delta B sub ij plus 1 minus delta all over n. And then the Markov chain will look like this. We will replace the matrix by M, but we know that M is delta B plus 1 minus delta all over n times a column matrix that includes 1. So therefore, the equation will be like this. So medyo mas complicated siya compared kay Alice, no? And the adjacency matrix will look like this for the second web graph, no? So if that's the case, we can write the probability transition matrix like this. And for this example, we will have a 1/6 for each value. That means you have a 1 over 6 chance of starting at that specific page. Okay, so let's compare. These are the values or the state vectors used by Alice, and then for Bob, these are the results, no? So what happened? If you will look here, there's a compared to Alice, no? 0 yung chance na mapunta ka sa page 4, 5, 6 kasi nga walang outgoing link to page 4, 5, and 6. Kaya 0 yung mga vectors, elements ng vectors na to. But for Bob, even if it's really small, no, there is a probability that you can go from page 1, 2, 3 to either page 4, 5, or 6. So, yun yung naging difference no strategy ni Bob from Alice. And that's the end of my report, no? So thank you. So I hope you understood what Markov chains are and appreciate how it can be used, especially in production of internet search engines. Thank you.